Morning, students. Myself, Mr. Vishal Gavas. I'm currently working as an assistant professor in Department of Mathematics, Government College, Khandola. And what we're gonna see today is how to count. Okay. Now, most of you must be wondering why would I need to teach you how to count, because you already know how to count. But there are certain things wherein we have to count smartly, to save our time and effort, in a lot of things. So, without wasting any more time, let's look at the topic for today. The topic for today is permutation and combinations, as you see it on the screen. Now, many of you must be unfamiliar with the territory, so let's do it slowly. Don't worry. Um, things would be refined. Okay, so let's start with the ideas. Okay, before that, let's look at a kind of a scenario, right, wherein we can understand what we are talking about. So let's suppose that we have a kind of a suitcase. Okay, and what we want to do is we want to open the suitcase, and the suitcase has a number lock. Okay, and suppose that we have forgotten its digits, right? There's a sequence, and the lock, as you all have seen, a briefcase with a number lock opens up when you put a correct order sequence, isn't it? Now, suppose we have forgotten the digits. Okay, but we remember the first digit, say suppose 4 digit, uh, and you all know that the digits vary from 0 to 9, say. So let's suppose that we remember the very first digit, say, so suppose 2. Then the question which is posed is how many sequences in together we might have to try. Uh, Now, since we already know the first digit, what we want to do is we want to find all the possible three three digit sequence, isn't it? So, but the problem here is how many three digit sequences you would try, because that will not, you cannot visualize that. You will have to list it down, you know and to count, it would take a lot of time and a lot of effort, you know. So this kind of counting, wherein you are arranging some things, listing down them, and then counting, takes a lot of time. Okay, so what we are going to see today is how do we count without we actually list them down. So let's begin with these ideas of countings. Okay, so we see here is an example of a person, Mr. Gopal, and what he wants to do is he wants to dress himself up, in a combination of pants and shirts. Okay, then the question is in how many ways he can dress up. Suppose he has three pants and two shirts at his disposal. How is it possible for him to dress himself in a different way, right? Then if we look at this, then the problem is pretty straightforward. If you have three pants and two shirts, right, then each pant he can wear two shirts, isn't it? So altogether, if he has three pants, then there would be exactly six possible ways he can dress him up, right? You can see that in the diagram. Like P1 is a pant, then he can wear S1 and S2 on P1, right? Again, P2 he can wear S1 and S2. Similarly, P3 again he can wear S1 and right? So if I look at this kind of counting, if he has three pants and two shirts, so if I choose the pant first, right, and then I want to wear a shirt, then I have three possibilities for shirt. Sorry, three possibilities for pants, two possibilities for shirts. Then altogether, what will happen is he will have 3 cross 2, you know, ways, right, of dressing himself. Now, if I look at this problem, this kind of principle, what we have just used, is called as fundamental principle of counting. Okay, so what does it say is if I have an event which can occur in m different ways, okay, and there's another event which can occur in n different ways following the event the previous event, right? Then the total number of occurrence of the events, both the events in a given order, is equal to m cross n. Right? So if I look at the previous problem, what happens is if I choose uh, depend as the event, first event, and choosing shirt as the second event, then first event can happen in three ways, second event can happen in two ways. So altogether, first and second event together in a order can happen in 3 cross 2, that was equal to 6, right? So let's see another example here. Okay, we would understand how do we use this fundamental principle of counting, right? Well, say suppose I have a word called as rock, right? I have a word rock, and what I want to do is I want to form different words, four-lettered words, okay, out of the alphabets of rock, right? But I want it in such a way that I am not repeating a single alphabet in a particular word. Okay, what I mean is, say suppose I have a four lettered word, then say suppose R comes in the first place, then R should not occur in any of the three possible letters, right? So there should not be any repetition of letters. So how many ways I can form, or how many words I can form out of the letters of row? Now this is very simple problem if you see on your screen. Okay, what the idea is you just start choosing each place, right? Say suppose I say that first place, right, of the word. If I look at here, right here, if I look at um, you know if I look at here, right, then this particular place, right, I have four letters, right, ROCK. Then this particular place can be chosen with any of these four letters, right? I can put any of these four letters here, right? So what happens is, if I take first event from this idea to be choosing the first place here, right, then there is four ways of occurring, right? If I look at once I choose the first letter, to choose the second letter, I would have only three possibilities, because once I choose one letter here, since the repetition of the letters are not allowed, this would have only three possible alphabets left with me because I've already chosen the first alphabet, right? Similarly, the third event would be having only two possibilities, because once I choose first and second event, third event of choosing the third alphabet would have only two possible outcomes, right? Or two possibilities rather. And once I choose one, two, three, fix fourth letter can be chosen in only one way, right? So if I look at the fundamental principle of counting, then it says that any event which occurs in m different way following which another event occurs in n different way and so on, then the total occurrence would be equal to m cross n. Now here there are four events. First event can occur in four ways, second event can occur in three ways, third event can occur in two ways, and the last event can occur in one way. So in together there would be 4 cross 3 cross 2 cross 1 number of, occurrence of them together. That means there will be exactly 24 words I can have out of the letters of, right? Now in case if the repetition was allowed, right, if they had said that the repetition would be allowed, then there would have been 4 cross 4 cross 4 cross 4 possible ways, isn't it? 4 cross 4 cross 4 cross 4 possible ways, right, of the that means there'll be 4 raised to 4 possible uh, words I can form, out of the alphabets of. Fine. Okay, let's look at the next example. Right now, what happens here is, if I just do the example here, I want to form a three-lettered words, right? If you can just pay attention to this example here, right? I want to form a three-letter word out of the word, or out of the alphabets of plumber, right? Now, what happens is if I do the same process of fundamental theorem of counting, then I want to form a three-lettered word, right? So I can choose. So if I look at the plumber word, I have seven alphabets altogether, isn't it? So if I want to form a three-lettered word, then first letter can be chosen in seven ways, right? If I look at here, second letter can be chosen, or second place can be chosen in six ways, and third can be chosen in 5 ways. Let me, I'm just finding only three places, right? Or three lettered words. So altogether what I'll have is I will have 7 cross 6 cross 5. That is exactly 210 different three lettered words, right? Isn't it? So if I look at these two examples, of course I've taken both the examples of choosing a alphabet. But if I see here that there's a specific order, so if I look at this arrangement, there is specific order. That means in way I'm choosing this alphabets kind of kind of matters, because if I change the order, I will get a different kind of object. For example, if I look at the idea of this first example, then what happens is if I choose R first, O later on, K third, and C fourth, right? Right, I get one word, and if I just change the order, that means I just reverse back. Okay, I choose C first, then K, then O, and then R. Then what happens is the total order, or the complete meaning of the word changes. That means what I get is I get two different kind of words. So just changing, or just changing the mere order of the occurrence of the words, or the way you choose the words, if you change that, what happens is your thing changes. You get a different kind of a thing, right? Such things, when the order matters, like in an arrangement, when the order matters, those kind of arrangements are called as permutation. So let's look at the formal definition of permutation. A permutation is an arrangement of in a definite order of a number of objects taken all or some at a time. Okay, what does it mean is you have a arrangement of letters or arrangement of any kind of thing in a definite order. Okay, wherein you take all the available objects, or you take some objects from the available objects. For example, if I look at this example of plumber, then what happens is I had seven numbers of I had a permutation of seven letters, but I was taking only three letters to form a three-lettered word. In the previous example, when I had the word rock, I was having four letters, and I was taking all the four letters to form different four-lettered words. So the first example was a permutation of four different things taken four at a time. Second example, it was like permutation of seven things taken three at a time, right? So in a permutation, what happens is your order of arrangement matters. If you change the order of arrangement, what happens is the object, right, becomes completely different. This is what you got to take in mind when you apply certain formulas for permutation. You got to see that what is the situation. If the situation demands the ordering, then you have to apply permutation. Is this fine? So let's look at the formulas for permutation. Okay, right. Before that, let's look at some notations. Okay, the thing which we gonna put formulas in, all the formulas of the permutation and combination, of course, would be taking something from factorial notation. Okay, now what is factorial notation? It's nothing but multiplication of numbers each time subtracting one from the previous one. Suppose you have a factorial of 2, then what you do is you take 2 first and subtract 1 from 2 till you reach 1. Okay? So 2 factorial would be equal to sub 1 from 2, that is 1. So the moment you reach 1, stop. Multiply everything. Get 2 cross 1, that is 2. 3 factorial would be you take 3, subtract 1 from 3, you get 2. Then subtract 1 from 2, you get 1. The moment you reach 1, stop the process, multiply everything. So what you have is 3. Similarly, 4 factorial will be take 4, then subtract 1 from 4, you get 3, subtract 1 from 3, you get 3, subtract 1 from 2, you get 1. The moment you reach 1, stop the process, keep multiplying everything which you have got, like 4 into 3 into 2 into 1, that will be equal to 24, and so on, right? So the factorial thing is just multiplication of numbers every time, subtracting 1 from the previous number till you reach 1. Is this clear, right? So let's put up the formulas for permutation. The first formula says that if you have n different objects, okay, take an r at a time, where r can be 0, that means you are not taking anything, right? Or you are taking everything, right? This is a problem here. You can also take 0, doesn't matter. But permutation of n objects taken r at a time, okay, is given by NPR. This is a notation. Okay, and this is the okay. So the permutations can be calculated. That means permutation of r different things taken. Sorry, permutation of n different things taken r at a time is given by n factorial upon n minus r factorial. Okay. Um, the next, and this is when the repetition is not allowed. Okay. When the repetition is allowed, the permutation of r different objects, permutation of n different objects rather taken r at a time is nothing but n cross n cross n cross m r times, right? That is nothing but n raised to r. And the last formula is permutation of n different objects where not all n are distinct. Okay. Say suppose there are p1 number of similar kind of objects, p2 are another similar kind of objects, and up to pk are another similar kind of objects, then the permutations of n objects, okay, in that case would be given by n factorial upon p1 factorial into p2 factorial so on up till pk factorial. Okay, so let's use these formulas to solve certain kind of problems. All right. So the first problem is we need to find the numbers, okay, lying between 100 to 1000, which can be formed from the digits 0, 1, 2, 3, 4, and 5, right? The 6 digits, okay, in which the repetition of any of these above digits are not allowed. Okay, now we need to understand certain things here, that if I look the digits from 100 to 1000, they are all 3 digits number. Okay, they are all 3 digit number. So the question here is we need to form a 3 digit number out of the digits which are available from 0, 1, 2, 3, 4, and 5. Now we need to take one thing in notice here, that if this numbers are taken, not all combination will give me a 3 digit number. For example, if I take 0 in the 100th place, right, then it won't be a 3 digit number. Are you getting my point? It would be not a 3 digit number in that case, right? So what happens is we have to take 0, and we have to make sure that 0 does not come in the 100th place, right? So to do this, what we do is uh, we take all the possible, first of all we'll take all the possible permutations of um 6 digits taken 3 at a time. Okay, and then subtract the possibility of two digits. Okay, now see, why we are using permutation, why this is a permutation kind of a problem is because the arrangement, the order of the arrangement matters here. Okay, because if I arrange these digits in certain order, I would get a different number. Okay, if I arrange it in another way, I get a different number. So the order of the arrangement matters here. Is this clear? So the solution of this is, what we're going to do is we'll first arrange all the possibility of 3 digit numbers. Okay, all the possible 3 digit number, and then subtract whatever the 2 digit number we are getting. Okay, so let's look at the solution. Okay, so what we do is we take all the 6 digits and we form 3 digit number. That means this is kind of a permutation of 6 objects taken 3 at a time. So what do we get is 6p3. Now 6p3, if you use the previous formula, right, it comes out to be 6 factorial upon 3 factorial, which comes out to be 120, right? So there'll be 120 possible arrangement of these 6 digits taken 3 at a time. But as I said, if I put 0 in the 100th place, what happens is, say suppose I get, if I take if I put 0 at the 100 place, then what I get is 0, 1, 2, right? Now 0, 1, 2 is nothing but 12, right, which is a 2 digit number. So we need to take out all these possibilities, isn't it, wherein the 0 comes in the I mean the possibilities when the 0 comes in the second, sorry, 100 place. So for that matter, what we do is we subtract the two digit numbers. So what we do is we remove 0, okay, and from 2 digit out of it. Okay, this is clear. So how many possible permutations I will have, right? So what I get is a permutation of 5 objects taken 2 at a time. Okay, so what I get is 5p. So what I do is I fix 0 in this 3 digit number, fix 0 in the 100 place, and then you look at the possible 2 digit numbers, right? So that means you remove 0, right, and find the remaining permutation of 5 digits, that is 5 digits taken 2 at a time. So it will be 5p2, right? And subtract 5p2 from 6p3, right? To get the two, I mean, to get the 3-digit number from 100 to 1000. That's what the problem is been done in this order, right? So what you get is 5p2 comes out to be 20, right? And what happens is 120 minus 20 gives you 100. So there are 100 3-digit numbers from 100 to 1000, which takes the digits from 0, 1, 2, 3, 4, and this is what we have in this problem. This is clear, right? Let's go to the next problem. Okay, now what we have is the question is how many ways I can arrange 3 red, 3 yellow, and 2 green discs in a row. Okay, if you are not able to distinguish between uh, the disc of the same color. Say suppose there are 4 discs, right? You cannot distinguish between the 4 red color discs. They all look alike, right? There are 3 yellow discs. Okay, they look alike as a matter of fact. And again, 2 green discs, they also look alike, right? So question is, in how many ways I can arrange this? So again, it's a kind of a permutation. Sorry, yeah, it's kind of a permutation problem. What I have is I have one, two, three objects, but they are not distinct together. They are of the same type, right? Some of them are kind of the same type. So red disc are of same type, yellow disc are of same type. So altogether, what happens is I have 9 objects. Okay. So in what way I can arrange these objects is given by the third formula, which we have already taken, isn't it? So the permutation of these 9 objects, isn't it, would be 9 factorial upon 4 factorial into 3 factorial into 2 factorial, which comes out to be 100 and sorry, 1260. Okay, this is clear because see, the formula, if you go back and check, let me take you to the formula again one more time. It says that if I look at here, then it says that there are certain kind of similar objects, isn't it, right? Certain kind of similar objects, right? Then this is the formula which we have to take. Is this fine, right? So let's go to the problem again. So that's what we have. It will be 9 factorial upon 4 factorial into 3 factorial into 2 factorial, and you calculate this. Now there's a kind of a trick here. Okay, it's not a trick, but if you look at the definition of factorial, now n factorial is nothing but n into n minus 1 into n minus 2, so on up till n minus k, whatever it is, and so on up till you reach 1. Okay, now what you need to take care here is, what happens is I can write this n factorial as n into n minus 1 factorial, right? Or n factorial can also be written as n into n minus 1 into n minus 2 factorial, right? Similarly, if I look at this 9 factorial can be written as 9 into 8 factorial, which again can be written as 9 into 8 into 7 factorial, which can be again written as 9 into 7 into 9 into 8 into 7 into 6 factorial, right? Or in other words, I can write 9 factorial as 9 into 8 into 7 into 6 into 5 into 4 factorial. Why I'm writing this? Because I can directly cancel 4 factorial from above, and that means in the numerator and as well as in the denominator, so that I get lesser number of calculations, right? Because if I do this in a kind of an examination, I won't have the calculator thing at my disposal, so I may not be able to calculate 9 factorial together, but I may be able to multiply smaller number of digits, right? So if you do these calculations, what you get is 1260 arrangement of this possible 9 disk. Okay, right? So let's go to the next problem. uh, Here again, what I want to do, so here what we want to do is we want to find a permutation of 8 different arrangements. Okay, right? The moment comes in an arrangement where the letters or digits are coming, it's without any doubt a permutation problem. Okay, so I want to find a permutation of 8 different lettered arrangements. Okay, wherein I'm using the letters or the alphabets from the word daughter. In First of all, I want to find in how many ways I can do this. Okay. Secondly, I want to find those kind of permutations or those kind of arrangement wherein all vowels from the word daughter are occurring together. And the second question is, I want to find those number of words in which vowels do not appear together. Okay. Now, it's a 8 letter arrangement. Okay, and I want to put the words from the daughter. Now, if I look at this word daughter, right, then every word is different here. Like if you see, it's a distinct word. I mean, it's a distinct lettered word, right? Isn't it? There's no uh, word repeating here. Okay, so it's not the third formula. It's a permutation question. Okay. Now, first of all, in how many ways I can form eight-letter words out of the words of daughter? It's exactly 8 into 7 into 6 into 4 into whatever. 8, 6, 8 into 7 into 6 into 5 into 4 and so on up till you reach 1. In other words, it's 8 factorial. So there'll be 8 factorial, possibly different words for the word daughter. From the word daughter, I can form 8 factorial number of different words, okay, in which repetition are not allowed. Okay. Now, what I want to find is in how many of these words vowels will occur together, right? Now, if I want to do that, then I have to find out what are the vowels in the word daughter, right? So if I have the idea of vowels, vowels are A, I, E, O, U, right? And the daughter has three vowels out of this, right? A is there, U is there, and E is there, isn't it? So if I want to put vowels together, I will have to make for the temporary basis it to be a one alphabet. A, U, E. Make sure that you take that as one alphabet, right? So if I take A, U, E as one alphabet, because you have to, it has to occur together, right? Then what happens is I have altogether how many alphabets? If you can check, I have eight alphabets, right? Out of which I take A, U, E as one alphabet, right? So three alphabets I remove to make it one, right? So what remains is five alphabet apart from A, U, E plus this as one alphabet because I'm taking it for the temporary purpose. So what I get is 6 factorial, isn't it? Right? I get 6 factorial, right? Sorry, or 6 uh, factorial arrangement of these words. Is this clear? Now there's a question in the arrangement of these vowels, because if I take it to be one arrangement, then what I can do is there are three letters A, U, E. I can again shuffle them among themselves because they have to occur together. Doesn't mean that they must be in specific kind of a thing, right? If you can just shuffle the order, like A can come first, U can come second, E can come third, or E can come first, U can come second, A can come third, right? Isn't it? So what happens, you can also make shuffle this in between them. So how many ways you can shuffle this? There are three letters and there are three places, so 3 factorial, of course. So you can shuffle the vowels among themselves in 3 factorial ways. So together what will happen is the number of words you will get, which will be in which vowels will be occurring together, would be exactly equal to 6 factorial multiplied by 3 factorial, that is equal to 4320 words. Okay. Now, if I want to find those words in which vowels are not occurring together, so if 4,320 words, I mean, there are 4,320 words in which vowels are occurring together, right? Then the words in which vowels are not occurring together can be found by subtracting this 4,320 from the total arrangements. And total arrangements, we have already seen that it's 8 factorial, right? So if you subtract 4320 from 8 factorial, what you get is 36,000. Okay. This clear, right? So let's go to the next idea. The next idea deals with something called as combinations. Okay. Now, so far we have seen the idea wherein we were counting in a specific order. There was a specific order assigned. Okay. Now the order is not assigned if the order is not there, or are we the way we count, in which we count, if the order is immaterial, right, then those kind, or what I'm saying in the arrangement of certain objects, right, if the order is immaterial, because if the order is changing, I count that as the same thing, say suppose, right, then they are not permutations anymore, because permutations, as we have seen, what happens is we are bothered about a specific arrangement, right? If the arrangement is changed, right, the counting is not one, there will be two different things, right? But there are certain things in which we are not required to follow a certain order. Say suppose A is one object, B is the second object. So if I choose A first and then take B, or take B first take A, it doesn't really matter. Okay, so those kind of things are called as combinations, okay, combinations of objects, and that's what we are gonna see in the next discussion. Is this clear? Right. So I hope permutation is clear. Let's look at combination. Okay, so let's look at the formal definition of combination. So combination is an arrangement of a number of objects taken some or all at a time without any regard to the order of the arrangement. Now, if I look at the definition of permutation, um, so if you look at the definition of permutation, then what happens is the definition changes here, right? When we say that regard to the order, they are in a specific given order, right? This order is mentioned. Now here there's without any regard to the order. That means the order is not relevant here, right? That kind of arrangements are called as combination, right? So if we look certain examples, so the question here is suppose I want to form a team of two players, right? And I have three lawn tennis players in my uh, at my disposal. Then in how many ways I can do this, right? Then if this question is to be answered, then I each time I can take two, right? Then if I have X, Y, Z as three team members, right? Then I can make X and Y in one. Now the problem here is I choose X first, Y later in this team, or Y first, X later in this team. I'm not gonna get a different team. I'm gonna get the same team, right? Similarly, if I take Y first, Z later, or Z first, Z first, Y later, does not really matter. Similarly, in the third case, right? So in this kind of counting, the order is immaterial, right? So order is there's no kind of special um, preference or the importance is given to the order, right? So those kind of arrangement wherein the order is immaterial is called as combination, right? Another example we can look at is uh, if suppose I have a I have 10 people, say suppose in a room, okay, in a room, and if all of them are shaking hands, then I want to count in how many ways or how many total handshakes I would have in that room, isn't it? If I want to do that, you want to count how many handshakes, right? Now, if two people are shaking hands with respect to the combination, X shaking hands with Y and Y shaking hands with X are not two different handshakes. They are the same handshake, right? Because these two people are shaking hands together, isn't it? So X shaking hands with Y and Y shaking hands with X is not a two different handshakes. They are same handshakes. So what will happen is the total number of handshakes would be the combination of 10 people, right, taken two at a time, isn't it? So there would be combination of 10 different objects taken two at a time. This is clear, right? So as what we have seen in the previous problems, let's look at the same kind of ideas, right, and the formulas in this thing or the combination as well. Okay, right? So let's look at this one. So the formula for combination, let's look at that. So the number of different combination of n different objects taken r at a time, okay, without repetition is denoted by NCR. That means combination of r objects taken n at combination of n objects taken r at a time, right? It was NPR in the previous case. Permutation of n objects taken r at a time. Here the combination of n objects taken are at a time. There are two notations, either of them can be used, okay, according to the convenience, right? So NCR is equal to n factorial upon r factorial upon n minus r factorial. Now there's r factorial. If I just hide this, if I just kind of hide this part from this, right, then what I get is exactly the formula for permutation, isn't it? So what happens is there's an extra thing which is divided, because we don't regard two things, we don't regard two things which are similar, right? X y y x are the same kind of combination for us, right? So those kind of things we are so whatever are repeating, we divide that to get the total number of combinations from total number of permutations, right? So that's the first thing. Secondly, that's what I was talking about, that NPR, if I see NPR is exactly equal to R factorial times NCR, right? That means if I just take R factorial to here, then what I get is NPR, isn't it? Then the third thing is taken as the combination of n objects taken zero at a time, okay, is one, okay, right? Now this can be regarded as in how many ways n objects from n objects. Okay, selecting r objects from n objects is same as rejecting n minus r objects, right? That's the next formula. That is selecting n objects from r objects, oh sorry, selecting r objects rather, I beg your pardon, selecting r objects from n objects, okay, is same as rejecting n minus r objects from the possible n objects, right? So if I look at the same ideas in NC0, right, then what happens is rejecting n objects from n objects. In how many ways I can do that? That's exactly just one way. Okay, so NC0 is taken to be 1. Okay, so this idea you have to take care in mind. And one more idea is, which I have not listed here, is 0 factorial. Okay, 0 factorial is taken to be 1. Okay, got to remember that 0 factorial is equal to 1, right? It's not 0, so don't be in that impression, right? 0 factorial is taken to be 1. So that's what I had to tell you. Let's straight away go to the problems. Okay, so the first problem here is, I want to form a committee of 4 persons, from 5 men and 5 women available. First of all, in how many ways this can be done? So how many committees I can have, right, from this availability of 10 people, in which the committee should consist of 4 persons. And in how many committees, in these committees, there will be exactly 1 man and 3 women. Okay, so this is what I want to find out, right? So this is again a combination problem, because when you choose a team or a committee or a certain kind of group, okay, then in the way you choose, it doesn't matter, group of people, okay, the way you choose, it doesn't matter, right? So these kind of things, wherein the when you arrange things, if suppose, the order does not matter, then it's just a combination uh, problem. So let's look at the solution. First of all, what happens is, I have 10 people, 5 men, 5 women. So altogether there are 10 people, and I want to choose 4 people at a time. So in how many ways I can do that? As many combinations of 10 people taken 4 at a time there would be, right? So the first answer is, there should be 10C4 number of possible number of committees, right? That is exactly 210 committees should be there in the setup, in this setup. Is this clear? Now I want to find in how many of these committees there would consist 1 man and 3 women, right? Now first of all, 4 people, I want 1 man, right, in this committee. 1 man, first of all, can be chosen from a availability of 5 men in 5C1 ways, isn't it? It's permutation of it's combination of one object, right, from possibly, oh sorry, it's combination of 5 objects, right, taken one at a time, isn't it? So it will be 5C1. Similarly, 3 women can be chosen from 5 women in 5C3 ways, isn't it? It's a combination of 5 women taken 3 at a time, isn't it? So in how many ways I can arrange 1 man and 3 women, right? First of all, there are choices of 5C1 for 1 man, right, and 5C3 of 3 women, right? So altogether, if I want to add them, see, what you want to understand is, when you have and, right, your combination gets multiplied, okay, and then if there's or, your combination gets added up, right? You need to see this. We'll see this in the next example, okay, but first, this time being, let's look at multiplications. If you look at the and 1 woman and 3 men, or 3 women and 1 man, and those kind of things, then you find the individual permutations, or sorry, if you find the individual combinations, right, and then multiply them, right? So here what happens is, I have 5C1 choices for 1 man, and I have 5C3 choices for 3 women. So the choices for 1 man and 3 women would be 5C1 multiplied by 5C3, right? So the total choices would be 5C1 multiplied by 5C3. That will be 50 committees would be there, in which there would be exactly 1 man and 3 women, right? And say suppose the question might have been that, in how many committees there would be no man, right? That means the committee should consist of entirely 4 women, right? Then in how many ways I can do this? I have 5 women, and then I have to choose 4 of them. In how many ways I can do? I can do it in 5C4 ways. That means there are exactly 5 committees in which there are no men. Is this fine? Right? So this is how the problems on these committee formations can be dealt with, right? Let's look at the next problem. Okay, right? So what we have is we have a deck of cards. Okay, and what I want to do is I want to find in how many ways, first of all, four cards can be chosen in pack of 52 cards, and in how many of these cards, these four cards, all the four cards will be of the same suit. And the second question is, in how many ways I can choose four face cards. Okay, right? So let's look at these ideas first. So when we have a pack of 52 cards, I have four suits first of all in them, right? That is spade, club, diamond, and heart, isn't it? Diamond and heart are of red colors. These two suits are of red colors, and club and spade are of black colors. So exactly there are two colors in this playing card, right? First of all, now there are 52 playing cards, and I have to choose four out of this, right? Then in how many ways I can do this is a question, right? How many ways I can choose four cards from 52 cards? This is just a, taking four cards, right? Without any kind of order. It doesn't matter which card I pick first, right? So it's a combination of 52 objects taken four at a time. That is 52 C4 ways, right? I can choose four cards from 52 available cards, right? Now, in how many ways I can choose four cards in the same suit? Now, you need to see that the suit is not mentioned, right? So, these four cards can be either of spade, this can be either of club, diamond, or heart, right? So, first would be exactly say how many ways I can choose four cards. That is exactly 27, 2,70,275. Okay, 2,70,275 choices are there of choosing four cards from play 52 playing cards, right? Now imagine listing them down and counting, right? That would be taking you maybe I don't know how many days, right? Now, to look at this first question in here, four cards out of the same suit can be chosen in how many ways, right? So, I can choose four cards from spade, or I can choose four cards from club. I can choose four cards from diamond, or I can also choose four cards from um hard, isn't it? So what happens is the total combinations that's what I said. Whenever there's or, the combinations gets added up, right? So I can choose 13 from sorry 4 from spade, that is 13 C4, or I can choose 13 from club, that is 13 C4 again, or I can choose 13 from diamond, that is 13 C4 again, or I can choose 13 C4 from heart, right? So what happens is your combination gets added up, right? So what happens is the total number of ways you can do this is exactly equal to 4 into 13 C4, which comes out to be 2,860. So there will be 2,860 combinations in which the four cards will be of the same suit. Is this clear? And the third question is asked that how many of these four cards will be face cards, right? Or how many possible ways I can choose four cards from, which will be all face cards. Now, you need to get the point here is there are altogether 12 face cards, right? Each suit has three face card, that is king, queen, and jack, right? So 12 face cards are there. In how many ways I can choose four face cards? And there's no order mentioned in the face card, right? So in how many ways I can choose four face cards from 12 exactly as 12 C4, right? So what are the number of combination in which these four cards will be all face cards? Exactly 495. So there will be 495 ways I can choose four face cards from 12 face cards. Is this clear? Right. So that's what we have in this kind of permutations. Okay, so that's it about the examples. I hope at least you have realized or understood certain things, and you can distinguish between when to use permutation. And that was the sole idea of this talk, that how do you distinguish between when do we use permutation and when do we use combination. Okay, the formula would follow, right? Problem with the applying formula, but the idea is when do you apply what formula, isn't it? So as far as the permutations are concerned, you just look at the scenario. If there's an order, like arrangement of words, arrangement of letters, arrangement of numbers, arrangement of something, which if you arrange in a certain way you get different thing, then it's permutation. And in arrangement, then where there's no order mentioned, like it's combination. So thank you, thanks a lot. I hope this discussion you must have found fruitful, and I hope that you have understood at least something out of this discussion, right? So thank you. Thanks a lot. That's it.